A modern manufacturing facility can generate thousands of data points per second. Sensors track vibration, temperature, and cycle counts, feeding constant streams of information into enterprise software. Yet, despite this massive surveillance, catastrophic reactive failures still routinely tear through the production line. When organizations face these unexpected breakdowns, the default response is often to increase the volume of data collection. They install more sensors, invest in newer monitoring software, and attempt to capture a wider net of information, assuming that a higher quantity of data will naturally illuminate the blind spots. But the root cause is rarely a lack of information. The environment is suffering from a data health deficit. Data exists in abundance, but because it cannot be trusted, compared, or acted upon, it functions as a liability rather than an asset. The consequences of this deficit are immediate. Schedules built on outdated records drive technicians to perform redundant maintenance. Erroneous entries lead to incorrect inventory levels, meaning critical spare parts are missing when needed. Outdated equipment logs result in missed warranty claims, shifting the financial burden directly back onto the operation. As these unforced errors accumulate, decision-makers lose confidence in the reports generated by their computerized maintenance management systems. When the data is unreliable, the software is abandoned, and the operation reverts to reactive, localized guesswork. Engineers secure data health through the ACCPRTT framework. This system isolates 7 required pillars of reliable information: accurate, complete, consistent, precise, relevant, timely, and transparent. These criteria function as a diagnostic tool and a structural pipeline designed to process raw inputs. By forcing information through these 7 specific filters, organizations systematically strip out the ambiguity and errors that cause system failures. Treating data health as a foundational infrastructure is the prerequisite for any advanced asset management. Before an organization can deploy predictive maintenance models, it must guarantee the integrity of the underlying pipeline. The structural pipeline begins at the input layer. This is the stage of data capture, where raw information from sensors, field inspections, and technicians first enters the system. To survive this initial entry point, data must pass 3 specific gates. The first requirement is accuracy. Accurate data is error-free information that strictly reflects physical reality. It ensures that the digital record exactly matches the physical machine on the floor. A large manufacturing plant recently audited its database and found that 15% of its asset register entries contained incorrect installation dates and mismatched serial numbers, driving unnecessary preventative maintenance tasks. By implementing automated barcode scanning that strictly validated physical tags against the digital record, they eliminated those errors at the point of entry and saved an estimated $120,000 annually. The second gate is completeness. Complete data means a record captures all required fields without omission. When failure codes, labor hours, or corrective actions are left blank, root cause analysis becomes mathematically impossible. To enforce this, a regional utility company reconfigured its maintenance software, turning optional work order details into mandatory fields. By refusing to let the system close a ticket until parts, labor, and failure codes were logged, they achieved 98% compliance in 6 months, restoring their ability to track recurring failures. The final input gate is precision. Precise data requires highly specific, actionable detail. Broad, vague textual descriptions like machine broken provide no analytical value to reliability engineers. A mining operation plagued by repeat equipment breakdowns replaced its open text maintenance logs with guided diagnostic prompts. Technicians were required to input exact locations, operating conditions, and observed symptoms. Armed with this exact detail, engineers identified the specific failure modes and reduced repeat breakdowns by 30% in the first year. By structurally enforcing accuracy, completeness, and precision at the exact moment of entry, organizations neutralize human error and omission before it can enter the database and pollute downstream analytics. Once data is captured accurately, it moves to the architecture layer. Raw facts are useless if they cannot be read by the entire organization. At this stage, information must be structured and filtered to ensure cross-system compatibility. This requires consistency. Consistent data maintains a single, uniform version of the truth across all databases, hierarchies, and measurement units. If maintenance software uses one naming convention and the enterprise resource planning system uses another, integration fails. The systems cannot recognize that they are looking at the same asset, which immediately generates duplicate records and reporting errors. An oil and gas operator managed assets across 3 different software platforms with varying naming conventions. By establishing a strict, standardized coding structure across all systems, they automatically eliminated over 1,200 duplicate records and reduced the time spent reconciling data by 40%. Structuring the data also demands relevance. Relevant data is strictly prioritized by the value it adds to decision-making. Information that does not drive an operational outcome is categorized as useless volume and discarded. For example, a facilities management team collected massive amounts of ambient light and humidity data that went entirely unused in their maintenance planning. By running a data usage review and archiving those irrelevant historical metrics, they reduced their data storage costs by 25% and cleared the clutter obscuring their critical performance metrics. Properly structuring data through consistency and relevance prevents system bloat. It ensures that complex software modules have a shared language, allowing them to actually communicate with each other. The final stage of the pipeline is delivery. Perfect data sitting dormant on a server yields no return on investment. The processed information must now be routed directly to the end users and management teams who dictate daily operations. This delivery must be timely. Timely data is current and available at the exact moment decisions need to be made, supporting real-time planning and rapid response. A logistics company was losing dispatch efficiency because technicians routinely waited 2 days to log job completions into the system. By deploying mobile devices integrated in real time with their maintenance software, they collapsed the data entry lag from 48 hours down to under 2 hours, instantly updating asset availability for the dispatch team. Finally, the delivery must be transparent. Transparent data means the information is highly visible, easily verifiable, and securely accessible across different operational silos. A hospital facility previously maintained separate, isolated engineering and reliability logs, which caused disputes over asset history. By migrating to a centralized, cloud-based system with clear open access rules, they eliminated duplicated maintenance tasks and allowed every department to verify the exact same operational history. Without timely and transparent delivery, the pipeline fails. Even perfectly accurate, highly structured data cannot improve operational agility or build cross-departmental trust if it is hidden in a silo or arrives a day too late. Understanding the architecture of this pipeline is only the first step. To generate actual reliability, an organization must operationalize these theories, translating the 7 ACCPRTT pillars into rigid daily system governance. This begins with establishing a data governance committee, a cross-functional team pulling stakeholders from IT, maintenance, and engineering to define the exact data standards. This committee must assign 2 distinct roles. The data owner holds the ultimate accountability for the accuracy of a specific dataset, like the asset register. The data steward executes the day-to-day management and quality checks, ensuring incoming data meets the required standards. But human willpower is an unreliable mechanism for data entry. Governance must be technologically enforced. The rules established by the committee have to be hard-coded directly into the enterprise software. This means configuring the maintenance software with mandatory field gating that blocks incomplete submissions, standardizing drop-down lists to prevent conflicting formats, and running automated error detection scripts to flag anomalies in real time. Once the system is built, it requires continuous monitoring. Organizations must track precise performance metrics to ensure the pipeline is actually functioning as designed. Management teams should isolate key performance indicators tied to the framework. They track the percentage of work orders closed with all mandatory fields completed, measure the average hourly lag between job completion and system entry, and count the exact number of duplicate assets detected each month. These metrics drive routine data audits, creating a strict feedback loop. When a random sample reveals inconsistent naming conventions, the stewards correct the errors, retrain the staff, and tighten the software validation rules, catching system degradation long before it corrupts the maintenance schedules. Maintaining high-quality data requires a permanent, system-enforced discipline. Rigorously applying the ACCPRTT framework replaces reactive chaos with a controlled, predictable system built on verifiable facts. When exact installation dates are known, when failure root causes are documented with precision, and when schedules update in real time, assets run exactly as engineered. Many organizations attempt to leap forward into digital transformation, investing in advanced analytics and machine learning. But those algorithms are entirely dependent on the quality of their training data. Feeding an advanced predictive model inaccurate or incomplete maintenance logs guarantees a flawed output. Standardizing this data through a rigid pipeline naturally creates a shared operational language. It aligns the maintenance technicians, the reliability engineers in control rooms, and executives planning capital investments. Ultimately, data health is asset health. Attempting to optimize physical reliability without first securing the integrity of the information pipeline is no longer an option. True operational excellence begins the moment you can absolutely trust your data.